Well, hello everybody. I work here, and this is such a privilege to welcome you to the place where I work, Roehampton University. It really is. It's so nice to see so many of you here. I need to say, all credit for today goes to Yasmin for putting such an amazing program together. People queried the slide title here. They said, surely you don't mean coding. You must mean programming or computer science, or better still, computing across the curriculum. The word is deliberately chosen, though, because I think, as Henrika says, we learn through making things, and there's a long heritage of that. Way, way back, if you can cast your mind back to before the 1st of September 2014, when we had the old ICT curriculum, we had this model of let's embed technology across the curriculum, that children will learn about using computers, will learn about computers through using tools like this and many, many others across the whole of the curriculum, that there are ways of using blogs and spreadsheets and Google Drive and Movie Maker and all of the rest in all of the subject domains. I think this did tremendously enrich learning within each of those subject domains. It extended, enriched, enhanced learning there. Was there enough opportunity to learn to use these tools? Well, in the best schools, yes, there was. Was there enough opportunity to develop an understanding of how these tools were made and the fundamental principles of computer science? Many of us argued perhaps there wasn't in that approach. And thus you get to the new computing curriculum. We start with this amazingly aspirational opening sentence: high-quality computing education equips pupils to use computational thinking and creativity to understand and change the world. That's fabulous, isn't it? But I think very often as computing educators, we stop reading when we get to the end of the word creativity there. Peter would argue when we get to the end of the word computational thinking, perhaps. There's a purpose to this. It is not an end in itself. It is about understanding the world. It is about changing the world. Assessing whether computing is working well in schools, simple. Ofsted, turn up, ask the child, have you understood the world? Have you changed the world? Yes, in both boxes. We can move on. Okay. The next sentence, though, is one which we generally don't look at. Computing has deep links with mathematics, science, design and technology, and I would argue many, many other domains, and provides insights into both natural and artificial systems. And it's that I'd like to focus on. How that we can take these ideas, these principles of computing and coding skills, and use them as a lens through which to understand other subjects. I've had to remove the logo from the slide there, but what's that? Okay, when they presented on how to inspect computing, this was one of the slides which David Brown showed. And it's that last bullet point which I think is really interesting. Well, there's that and the previous one. Context in which computing is taught are relevant to pupils' lives and reflect the increasing use of computing in the industry, links forged with other agencies and the wider community. And then the last bullet point, links with other subjects in the school are productive in strengthening pupils' learning in computing. He said, your computing curriculum is not good or outstanding. In other words, it requires improvement if it doesn't do that. Sorry, too many negatives in the sentence there. We've got Barefoot Computing here in the terrace room. Go and visit them at the coffee break. For Barefoot Computing, we took the models, primary school CPD program, that primary school teachers knew how to teach. They knew how to use technology. They didn't understand much computer science. We may or may not have been wrong. And we said, this is about computational thinking. This is about applying the principles of computer science in the context of other subjects. So you have there, as fundamental concepts to computer science, the notion of logic, the notion of algorithms, sequences of steps, sets of rules, of breaking problems down into smaller parts, of looking for patterns, looking for generalizations, of managing complexity. I love the notion of human resource machine, I really do. And of evaluating, of stepping back and seeing whether what we've done works. None of this is unique to computing. Of course it isn't. You want children using logical reasoning across the curriculum. Children are given a project to do. Of course they've got to manage complexity. Of course they've got to break that down. And we've developed resources around that. We also, though, have a cluster of approaches there. And it's worth just thinking about those and why they perhaps don't get as much attention as those concepts. About playing, experimenting, tinkering, as we called it. About making things, creating. About fixing things when they go wrong. Again, this is something which applies across the curriculum, of Of course it does. It's not just a computer science thing. And so, for barefoot and for other things, we've got lovely examples like that. Jane Waite's lovely idea of looking at phonics as a set of rules. The or sound can be represented in a number of different grapheme ways. Reference to phonics at Roehampton, who'd have thought it, hey? And we have the classification key in science. It's a binary tree. It's yes or no questions. Yes, this is a computational thinking idea. Making pizza, pizza. We've got a whole set of steps to follow. You break down that big problem. Making things, putting on a play, let's put on a musical. All of that is great. And those applications of computational thinking across the curriculum, other people speak very eloquently about. That's not what I want to talk about in the few minutes that are left. I want to come back to where Papert was back in 1980, that he saw how the children who'd learnt to program computers started looking at problems, started looking at systems in a different way. That by learning how to move the turtle across the floor, to draw the triangle, to draw the house shape, they started seeing geometry differently. Their understanding of mathematics was enhanced through their learning of computer programming, of coding, not merely computational thinking applied in the domain of, okay? So this is, as I say, about coding. All right, the rapid tour now. Okay, how many subjects on the curriculum? Let's see how many we can tick off before coffee time, hey? So, English, and I said coding because by saying coding rather than programming, I'm allowed to bring in HTML. It's not writing a program, but it is writing language in a code which the computer can understand. What would you learn about English through working in HTML? Surely they ought to be handwriting. Surely they ought to be, using a word processor. Well, perhaps they should. But by working in HTML, you stop worrying about what font you're going to put it in and start focusing on the structure of the document there. You think about what is a paragraph? What's another paragraph? What are the bullet points? You think about providing the supporting evidence. Berners-Lee's great insight. The birth of the web was about linking documents together, not just writing your thing, but linking back to where those ideas came from. We encourage our students to do that at Roehampton. I've got Pete Kemp in the room. He can speak about this far more eloquently. You have storytelling. Your power to tell a story in English. Of course you can do the drama. Of course you can write the story. But you can also make the 3D animated film which tells the story. We don't have lots of time, but it's worth playing this because it is fabulous. Very sad somehow, isn't it? But do those students, those 4 18-year-olds, is it, Pete, learn about creative writing through putting together a film like that? I'd say they do. It's another medium for their creative expression, and that's drawing on code, of course it is. Okay, what about mathematics, my own subject? Well, if you were sat a little closer to the screen, or the screen was a bit bigger, I'd say, what does this code do here? This is Scratch, lovely building block-based programming language, and lots of children at primary school write games and animations in Scratch. The one on screen here isn't a game. The one on screen here is going to put 1,000,000 dots on the screen and test whether they're within 180 units of the center of the screen. If they are, it colors them in one way. If they're not, it colors them in the other way. Let's set the thing going, and we'll see how we do there. That's 50 dots already. I said 1,000,000 dots. Okay, let's speed the thing up here. Okay, edit, go into turbo mode. And you see that anything which is less than 180 units from the center of the screen colors in green. Everything else in that square colors in blue. What's the area of the square? What is the fraction of the dots which are green out of the fraction of the number of dots we've plotted? But what's the area of that shape? Something pi r squared, am I hearing? Yeah? So we have here a practical way of estimating the value of pi. And computer says 3.143888. Oh, well, it was close enough, wasn't it? Yeah? And what a lovely way to illustrate that point, I would argue. Okay, another example from maths. Here we've got fractions, everybody's favourite topic, primary and secondary maths curriculum. Let's see if we can make that a little bit bigger for you. We've got Python code on the screen here. This defines a function. This is Euclid's algorithm for working out the highest common factor of a pair of numbers. This is, I think, the oldest recorded algorithm in history. Euclid did it in terms of length. If we fire off the code and see, we can start typing in some values. HCF of 24 and 16 should be 8. Are we optimistic, folks? Yes, it worked. We can then use that idea and define a whole class in Python of fractions arithmetic. And if you're worried about motivating contexts for teaching object-oriented programming, then developing a system for fractions arithmetic, I think, is as good as any, and then I can give it sums to do. So I can say print the answer to fraction, I don't know, 2/3 plus fraction 1/4. Anybody in the room? 2/3 plus a quarter? Okay, 11/12, let's hope so. Oops, type error. I hate it when it does that. Okay, that's me. Don't do live demos, folks. And there you get the 11/12, which we were confidently predicted there. Okay, I've written a program which can do fractions arithmetic. Wow, I can now stop doing fractions arithmetic and make my computer do fractions arithmetic. Well, you could, but I'd argue that writing the program to do that, once your programming skills are good enough, really shows whether you understand how fractions arithmetic works. We teach them the algorithm for doing fractions arithmetic. Why not implement that algorithm as code on a digital device such as the one in front of me here? That was the example you've just seen. What about science? You have the classification key. It's a lovely example of a binary tree. I do a lot of the game-based learning thing too, and so, as well as struggle to make presentation software work. So you've got that idea of the choose your own adventure, and Livingston lives just up there. Do you want to fight the dragon, turn to page 92? Do you want to run away from the dragon, turn to page 106? It's exactly the same structure as a graph, as an algorithm, as the classification keys. So let's create the thing. I'm thinking of a mini beast. Does it have legs? This is a snail, by the way. Does it have legs? No, it doesn't. Is it long and segmented? No, it isn't. Does it have a shell? Yes, it does. I have a snail. Yeah. Okay, working through a classification key, that's really exciting. Writing a program to implement a classification key, I would argue that that develops children's understanding of that in a way which wouldn't otherwise. Classic example from science education of artificial life, Conway's game of life here. The rules are very, very simple for Conway's game of life. You work on a grid, you can do it with pencil and paper if you really want. Any living cell with 2 live neighbours dies because there's not enough people around. Any live cell with 2 or 3, less than 2 cells, dies. 2 or 3 cells, it survives. More than 3 cells, it dies because of overpopulation. Dead cell with 3 live neighbours becomes alive as if by reproduction. Very, very simple rules. Implementing that as code is not actually that straightforward, but you can do it. I'm using NumPy as a way of doing that here. We can create our own board there. So true is where there's a live cell. We can move forward 1 cell at a time, or at least I thought we could. Okay. Oh yes, that's fine, and we get that's moving on. We then have a large block of code here, which I'm not going to walk you through, which sets up the animation of the thing, and then we can see what happens to this population 1 generation after the next, and here it goes. Let's play the thing and see. So that's applying those rules to that grid of squares, and I think after 8 generations it becomes a stable space with just those 8 cells alive. We can create our own pattern here. Notice the binary code here and see what happens to that. So that sets it up on the cell, and let's have a look at what happens to that when we set it running. And they're using those very, very simple rules. We've developed something which looks as though it's flying, or at least moving, as a cellular automata. Okay, what else have we got? Over into art and design, this notion of the fractal nature of nature, really. Draw a tree. How do you draw a tree? Do you notice when you look at a tree that each of the branches looks a little bit like the whole tree? Ferns are really good at this. Broccoli is really good at that. Writing this code in Scratch is not too difficult. So here we go inside the program there. Let's have a look at those a little bit bigger. So every time the tree command here is made up of two other tree commands, and it keeps saying draw another tree until the trees get really, really small. Again, we'll switch turbo mode on and let the thing run. Isn't that gorgeous? Turtle graphics, using nothing more sophisticated than moving and turning, and we get something which looks a lot like a tree. Other examples from art and design. Okay, so photography. I'm not claiming this is a brilliant photograph here, but can you tell me what has happened to my photograph in this first diagram, top left? Is it got a green square on it? Absolutely, yes. Okay, it is ever so slightly disturbing that only one of you noticed. But what's happened to the data that describes that diagram? I could, of course, go into Photoshop and draw a green square on top, but I can also, and this is how I made these pictures, go into Python and use a library and start manipulating the individual bytes which make up these images. What about this one here? What's happened to that? Very good. Tree in Australia, spot on. And what again, what's the binary going on there? What's happening to the bytes that make up that image? Well, what I'm doing with the code is starting at the bottom right rather than the top left and just replacing the bytes in the image with the one from the opposite corner. This one here, I'm taking the value of each byte, subtracting it away from 255 and storing that as a new image. And that gives me a photographic negative. I can't be the only person old enough in the room to remember photographic negatives. Okay. This one here, again, the binary manipulation of this is really interesting, because what you're doing there to produce the black and white image is simply taking the average of the red, green, and blue values and storing those numbers in each of those 3 bytes, and that gives you the grayscale image. I'm conscious of time passing, so you don't get to see the code on that one at the moment. Okay, it's there if you want. What about design and technology? So many opportunities. Fabulous, fabulous opportunities to use coding in the design and technology curriculum, of getting children to create products, and then build some intelligence or some autonomy into those. And the BBC Microbit would be my platform of choice there. There's also fabulous stuff from Lego, and of course the Raspberry Pi is well worth acknowledging if your project is going to be a more ambitious one still. Yeah, we had this wonderful launch event at Haberdashers Asks Boys School last Friday, where they created their robot and popped the the microbit into the top and then trundled around solving the maze that they had there. And again, in design and technology, so many opportunities to link this with the semi-ubiquitous Minecraft, of course. We have there in the computing curriculum, children should learn about Boolean logic. As far as I can tell, the best way to teach that is to develop things with redstone in Minecraft and actually have them build the logic gates. Really difficult to do that with silicon. Very, very easy to do it inside Minecraft world. And of course, for the Raspberry Pi edition of Minecraft, you have the ability to code that to make the 1,000 block size mega block of TNT there, and see what happens if you set fire to that. That's left as an exercise. Okay, I promised you coding. This isn't coding. This is the idea of the finite state machine. And of course, all of you are tremendously excited about the finite state machine. We have the finite state machine as applied to sentences in English. You follow the arrows through and you get a grammatically correct English sentence, that there are rules of grammar which we can treat in a computational way. But you can apply that same idea to other languages. There are more languages available than just English. So we can do French, we can do Polish, and it's a very, very similar structure to their finite state machine sentence generators as it is to ours. Not all languages work the same way. We're getting at deep notions of Chomskyan pre-grammar and things like that. Scratch has the language packs built in. If you have a child whose first language is not English, let them program Scratch using their mother tongue. Why not? Of course, it's important that they learn to speak English, but give them one lesson a week. where they can work in their own language. So do you remember, was it Ian Livingstone or Alex Hope saying, coding is the new Latin, way back, sort of 3 years ago? We've now got to the point where Latin is the new coding, in fact. It's program scratch in Latin. I was disappointed that it didn't move the numbers into Roman numerals, because that's really important in the maths curriculum. Okay. You have so many lovely opportunities in geography education. I focused on weather. The Raspberry Pi has this amazing weather station, which plug the sensors into your Raspberry Pi and it beams the data out there onto the internet. But you can also get the data from the internet. So you can do data analysis using big climate data. So the Met Office have data available from Heathrow and a number of other weather stations stretching back a significant number of years, I think back as far as 1848 here. So we'll read that in as a spreadsheet. And there you go. We've got 890 individual weather records stretching back to 1948 here. It's the average daily maximum temperature for a month, and the similar sorts of things in the other column there. What can we do with that? Well, we can ask Python here to work out the mean of those and the mean of the minimum temperatures. We can look at standard deviations if we're interested. We can plot a chart. Try doing histograms in Excel. It's painful. Try doing it in Pandas, which is this library for Python, and it works with just a single line of code there. Developing an understanding of code, but also developing an understanding of weather. We can do a scatter plot. And bizarrely, you find that the sunnier months were also the warmer months. Who knew? Okay. We can tidy up the data. We can look at what the weather was like 6 years ago in June 2010. So we had those sorts of figures then. We can have a look at when all the cold months were from that. What's a cold month? It's one where the minimum temperature is below zero or there are more than 15 frost days, and that's your list of that. We can have a look at how those minimum temperatures have changed over time. And surprisingly enough, you get a very periodic graph that the summer is warmer than the winter. We can do the same thing with maximum temperatures here. And again, you get that same sort of picture. Would you say, looking at those graphs, there's any truth in this global warming thing, just from the data? It's a little too noisy, isn't it? It's a little hard to tell. What can we do? Well, we can take a rolling average of this, averaging those monthly minimums, monthly maximums over a period of 60 months. That's 5 years, and then plotting that. This is the 5-year rolling average of minimum temperatures. I think the data says something there. And through doing that coding, the child learns something in the domain of geography. Yasmin, it's 10:30. Do you want me to stop or go on a little bit? Go on a little bit. Okay, so key stage 1 of the primary history curriculum, it says compare two historical figures. And one of the examples it gives is William Caxton and Tim Berners-Lee. William Caxton brought printing to the UK, Berners-Lee, creator of the World Wide Web. What were the similar challenges? What were the similar experiences there? I'm not talking about coding, but it's a tremendous insight into this idea of communication, this idea of liberalizing, of democratizing the spread of knowledge, that then in Caxton Day, anybody who could read could suddenly acquire knowledge in a way which hitherto had been impossible. Now in Berners-Lee's time, anybody who can write and connect to the web can communicate with an audience of 3 billion other people. In Caxton's time, the stationer's company controlled what happened. In Berners-Lee time, I don't know. What happens there? And then, of course, so in terms of history of information, history of cryptography is a lovely topic to look at through the ages, right from Roman times, right up to the present day with dual key, public-private key cryptographic systems. Enigma, of course, is a significant event in British history, but also lots and lots of other opportunities to give children an experience of writing some code to explore cryptographic ideas. In music education, of course, something like Sonic Pi, as well as, of course, composing using digital technology. But here I'm writing a program which plays a piece of music. No comment on my own personal position on Brexit was implied by that, of course. You could do the same thing in Scratch. In PE, what are the opportunities to do coding in PE, Mars? Well, I'm wearing something which keeps track of the state of my fitness. Oh dear, that's not going to be good data to analyse. Get the raw data. What's happening here? What's happening here? What's happening here? What does the accelerometer data from a Fitbit or a microbit tell you about what the person was doing at that particular time when they had that on their wrist? And of course, a lovely, lovely opportunity to link this with the Kinect sensor for the Xbox, plug that into Scratch. You have the whole Kinect to Scratch thing going on, and you can do the dance moves and get that to control your game or whatever. PHSE and citizenship, again, not so much on the coding, although the insights are powerful. British Library, a year ago, for the Magna Carta anniversary, asked young people, what do you most care about? What should be the rights today in terms of online digital rights? These were the top 10 that they voted for. And there's an issue in survey design here, isn't there? Allow freedom of speech. Be free from government censors. Not allow any kind of government censorship. Be free from censorship and mass surveillance. Have freedom of speech. Not be censored by the government. These were the statements which were voted for by young people. This seems to be something which they really do care about. What are the challenges there? What are the issues there? What do you think about? And more to the point, what do your pupils think about the draft investigatory powers bill? Is it just, imagine living in a regime where every use you make of technology, where every website you visit is logged and monitored by those placed in authority. North Korea? UK under the draft investigatory powers bill? Or most schools today? Yeah? We do this for the right reasons. Of course we do this for the right reasons, to protect our young people from people who wish them harm. But at what expense to rights and liberty and things like that? RE, coding in RE maths. I think there's such a lot of lovely opportunities to explore Islamic art. Not just the patterns, but the idea behind Islamic art, as why in Islamic art you don't see representations of people or of animals, why it is it's almost entirely a geometrical medium, and we can write Scratch code to do that too, which I'm not going to show you now. The next slide would be good. And also, of course, some of those ethical questions. We're at the point now where a computer has kind of passed the Turing test. It managed to fake the idea that it was an Eastern European teenager who didn't speak English very well. And the person asking the questions in the Turing test was convinced by that. How much longer before a machine says it is conscious? If a machine says it is conscious, is it conscious? I tell you, I'm conscious. It doesn't necessarily mean that. Yeah. What rights? What are the ethical questions when we have a machine which claims to think, that claims to be conscious? Would you switch that off? I think most of us would feel we ought to think about that at least. Right, so questions. I think we're going to do that over coffee, over in the terrace room, rather than doing that now. Is it coffee now? It is coffee now, but thank you all very much.